And kind of the most important distinction between the two is to understand the difference between something they call a parameter and something they call a statistic. And the thing that's really easy to distinguish is because of the letters they start with, it's easy to remember which one's which. So, first of all, I want you to know that a parameter is coming from the population. And second, a statistic always comes from a sample. So P with P, S with S. Super easy to remember. But very important to understand the differences. In your work, when you're talking about sampling distributions, you need to understand that whenever you talk about populations, you use certain symbols, and whenever you talk about samples, you use other symbols. So down below here, they have a list of symbols that you'll be using when you're talking about populations. And you can see that we have mu, sigma, and, sorry, can't see the other thing, p for the proportion. And then for samples, we have x bar, s, and p hat, which stands for the sample proportion. The proportion, again, is that decimal representation of the area under the curve, the probability, the percentages, that kind of thing. Questions on any of those? And a crowbar. Okay.
Is that a crowbar?
In this next part, we have an example, so just to talk about which things are which. We're going to try and figure out what the population is, the parameter, the sample, and the statistic in each of these examples. So in letter A, we have a pedestrian who wants to know the 75th percentile for the distribution of heights of 10-year-old boys. So she takes a sample of 50 patients and calculates Q3 to be 56 inches. So first, let's talk about the population. What's the population? 10-year-old boys, very good. 10-year-old boys. Aaron. And then next, let's talk about the parameter. Remember the parameter. Let's talk about the parameter.
Percentile.
75th percentile. How about then, the next thing was they want to know what the sample was going to be. What was that?
50 patients.
50 patients. And then the last thing was the statistic. Yep, that Q3 was equal to 56 inches. Okay, let's try again. So the first thing is, what's the population?
17-year-old boys.
I like that. I'm going to use one more word. All 12 to 17-year-old boys?
No, just
Olds. Thank you. Second, the parameter. I think this one's a little bit tricky, actually.
yeah. They're not bad, so.
Yep. So the way we're going to say it, it's kind of, they don't give us a number like in the last one. So this is
Have 100%.
the proportion, because remember, proportion has to do with parameter, right? And I'm just going to put P of cell phone owners. Is that what they talked about, right? Cell phone? Of kids, I probably should say 12 to 17-year-olds, with cell phones. So this one's kind of weird because they don't actually say what it is, but it's always the proportion, P, not P hat, P. Next. Actually, I'll use brown. The next one was the sample, 1102. 12 to 17-year-old respondents, right? Is that what they said?
Or, yeah, respondents.
respondents. I use the word respondents, I'll use the same. Respondents. And then the last one is the statistic, which is probably the easiest one to find. That's the p hat, or the proportion of 0.71.
Should we write it as a decimal?
Yes, if you're using the letter P, use a decimal. Remember, only use percentages if they ask for percentages. Otherwise, use the decimal representation. So on this next slide, we're going to talk about variability. And sampling variability is the value of a statistic and how it varies when you have repeated random samples. So we talked about in our class, we could have flipping coins, and Sam could flip a coin 10 times and see 7 heads, and Lydia could do it and see 2. Okay, and those are 2 different samples. And we happen to know that since they're equally likely events, that we should see half or 5 of those 10 turn out. And so what we do is we take lots of samples, and the sampling variability is talking about your statistics can change sample to sample. Oh, they even talked about it, sorry. If you were to flip a coin 50 times and count the number of heads you got, not everybody gets the same value. And then because that happens, we take lots of samples. In a distribution, the sampling distribution is the distribution of values taken by the statistic in all possible samples. All possible samples, that's kind of important. So let's circle that. All possible samples of the same size from the population. It's almost impossible to take all the possible samples, of course, of some size n. Instead, we use simulations to take many different samples. A population distribution is the values of the variable for all the individuals in that population. So one is the samples, and one is individuals. And again, you have the keywords. Sampling distribution come from samples. Population distribution, when you talk about a population, that means everybody. And so that's individuals, everybody. Okay, not samples. Down below here, we have an example. We use some statistical software to simulate 500 simple random samples. Each of these samples was 20 large. Okay, so I take a sample of 20, and I do it again, and I do it again, and I do it again. I do that 500 times. There are 200 chips that I'm drawing from when I take my sample. 100 of them are red, and 100 are blue. Down below, there's a dot plot. You can't really see it. It kind of almost looks like a bar graph, but it's a dot plot of all the different values of P, which remember is the sample proportion of the red chips in this case, because they're talking about the red chips. Is this the sampling distribution? Go back and look. Read sampling distribution. Are they from samples? Yes. Are they from all of the possible samples? No. How many did they take? 500. Do you think there are only 500 possibilities with 200 chips? No. So the answer to this question, it seems kind of strange maybe, but the answer is no. Although this represents a distribution, distribution of samples, it is not all possible samples. And that's why the answer is no. So it's of samples, but not all the samples. In part B, what do you notice about our socks? What about the shape? Looks like it's relatively normal. So our shape seems to be symmetric. What was the next one? Oh, outliers. To me, this looks a little shady, so maybe that's an outlier. I don't know. Perhaps the p hat of, is that 0.15? Is an outlier. That's a possibility. And maybe you might want to talk about how it's centered. It looks like the mean, median is 0.5 for the p hat, to me. And the vast majority of our values look like, I don't know, they're between 0.35 and 0.65 maybe. So you could write that too. I ran out of room, but maybe you could write something like that. I think those three are probably the most important. Oh, spread. So maybe that's where I would talk about it. Okay, so let me write that off to this. Okay, so the last part that we didn't mention earlier, which I'm repeating because I didn't have my recorder on, is that in the spread, if you were to mention something, it looks like to me that the vast majority of our observations occur between 0.35 and 0.65 for our sample proportion. Thank you. Okay, and this last question says you have a teacher with a bag of potato chips. They claim that half of them are red. Somebody takes a simple random sample of 20 and you find out 17 of them are red. What do you conclude about the claim? So first of all, you should know that your p hat, because it's a sample, was 17 out of 20, which is 0.85, if that helps for people who are not as comfortable with fractions. And if we claim that we have half of them being red, this result seems unlikely if half the chips should be red. What did you say, Sam?
Doesn't even appear in the graph.
And
Out of 500 trials.
out
Population.
of 500 samples, none were greater than 0.8. The teacher's claim is likely false. Or, I guess I would say, bogus. Okay, in this next slide, we're going to talk about population distributions, distributions of sample data, sampling distribution, and we should know the differences between the two, or three, I should say. There are some pictures, so it's kind of hard for me to see in this screen. I'm sorry if it's hard for you to see as well. Off to the left, we have population distributions, and so you'll see that in population distributions. Here, for example, they had like the chips. There were 200 total chips, 100 blue, 100 red. And off to the side, you'll see frequency. Then sample data, if you look in the middle, and I can't really tell what those little numbers are, but it looks like they talk about SRSs in each single one. N is 20. Whenever they say SRS, you know it's a sample because that stands for simple random sample. Notice how they talk about the numbers here, and again on the side there are frequencies.